Once again, a very warm welcome to you, sir. I now request you, sir, to kindly continue with the today's session.
Thank you so much, Nitin sir. Uh, yeah, so I hope like everybody has joined. So I'll share my screen and we'll start from where we have ended yesterday. Just give me a minute. Let me just share my screen. So, a very good evening to all of the participants, respected faculty members from the university. Once again, my heartfelt gratitude and thanks for inviting me as like the guest lecturer here to share my experience and my little bit knowledge that I have for the software with all you all. And I would really appreciate and love to work with any of you who is interested in working with solar cell domain, specifically working for this software. How it works, we talked yesterday. So again, today I'll start from there only, but there were few things that were left yesterday, which needs to be um, talked about also. So I'll take them one by one. Actually, some more information is required for the software to work according to your requirements. Like yesterday, we specifically talked about the material properties that needs to be fed by the user, right? Like say for example, I was talking about mine work wherein I was working with copper zinc tin sulfide. So I worked upon those three materials and then I got all those values and put in here to get the simulation. But it is not only these material properties which are important, but also there are a few other factors also. One of them was this the thickness of the material you are using. So yesterday I show you that if you change the material thickness, specifically the absorber layer material, there was a certain change in the solar cell parameters. So likewise, it is not only one layer's thickness that we can change thickness for all the layers. Like I'll show you for the device that I was talking yesterday. Okay, so the same device I talked about yesterday. So there we saw this 2 micron, and then somebody asked that how it works and how this change affects our simulation and all. So this we can do. Similar way, we can change the thickness of other materials layer as well. Like here, this zinc selenium, which is an N-type material here.
Sir,
So this property can
your
Sir, your
presentation is
screen
not
is not visible.
not visible. Okay. Thank you, sir. Thanks for letting me know. I hope now it is visible.
yes, yes.
Yeah, sorry. So I was talking that not only that absorber layer thickness, but also the other layers. So here that I have used this ZnSe, which is zinc selenide. So these layer thickness also can be changed, and accordingly, the effect on our simulations can be seen. Okay, so I'll accept this and all. Now coming back to, there were some few more calculations. Okay, so if you can see here, yeah. So um, this portal we talked about yesterday a lot. that these are certain end and initial points that we need to figure it out. Once we start working, we just go on for hit and trial that what could be these values, and once we find out our optimized value, we can get it that. But then talking about this elimination part, I told like I didn't talked about what is illumination and how it all. I just talked that we need to give the ambience of sunlight for our solar cell to be simulated here. Now, how does that ambience is created? The question is this. So definitely in a software we cannot provide sunlight. So but whatever sunlight provides to the solar cell, that can be materialized in form of certain data, and that can be given to the software. So what is that? That is a very specific file called as spectrum file. A spectrum, we all are aware of. A spectrum is the when we talk solar spectrum, means the solar light variation from one frequency to other or one wavelength to the other. So that sort of data we need to collect and give it to our software. So for all these solar cells that we are using in on terrestrial grounds, needs to be given AM 1.5G. It's a standard spectrum which we give for for simulation purpose, and that is AM 1.5G. Okay, so now how do we, by default, when we just start the SCAP software, you can see here, like the software has been, I have installed the software in my C drive, so it is the path there, and you can see that there is a folder named Spectrum, and there this by default AM 1.5G spectrum has been selected, and this will be used. So if we wish to see what is this spectrum file, we can see it there. So this AM 1.5G spectrum has 1000 watts per meter square. It is this the intensity of this spectrum is this. Now, the question is that when we do research not only for terrestrial solar cells, but for other, like many a times we do work for solar cell that can be used like other than terrestrial applications. So for such things, we need to change the spectrum. So again, Professor Bergelman has already inculcated these such so many spectrum files. So you can see that in SCAPS folder, which will be auto created in the directory where you are installing the software, you can see there will be a spectrum folder on also, and that spectrum folder will contain all the possible, or rather all the used spectrum files. You can see then this one AM 1.5 is there, AM 1.5G spectrum is there, then AM 1.5D spectrum is there, and then there are certain AM 0 spectrum is there. So these, they all have their own meaning depending on what research you are doing and what solar cell you are working with. We can choose them all, not all, but one of them. Sorry, and then we have certain specific spectrum files also, like a spectrum file for 450 nanometer of solar spectrum, and then 300, 400. So depending on what we usually use, so these spectrum files are there in another folder. Now what happens that sometimes we want to give our own spectrum file, so that we can give without problem. The only thing is that you have to create that spec file in a notepad, and then get it like in the same folder where this spectrum part is there. So from there we can select it, like we have this white light spectrum file also. So I would like to you to have a understanding of the spectrum files also. So okay, okay, spectrum. So you can see this is the folder. I'll go back. In my program file, there is this SCAPS folder is created, and in this you can see there are lots of other, and one of them is the spectrum file. So all those files that were visible to be checked upon to be taken there in the software is present here. So if you want to see what is this 1.5G, you can just click on it. You can open it with Notepad. Okay, so that 1.5 spectrum has this kind of data inside the file, where the left hand side is the wavelength, lambda in nanometers, and this is the corresponding power, that is watt per meter square. Okay, so if anybody wants to use or create their own spectrum file with the literature, we all can create it. We just have to put the data in this format. Okay, and then just create it and put it in the same folder, and from there we can use it in our SCAP simulation. Okay, so this I wanted to show you all. Okay, let's go back to our previous part. Okay, so now I hope everybody is clear with this. What is this spectrum and what is how this file is selected. Also, you can change it according to our requirement. So this is one of the very important aspect when we do simulations on solar cell using this CAP software. Okay, so many times we are also interested in dark illumination. Like you all must be aware with the solar cell, that even if there is no light present, there is very slight uh, so there is very light current in the circuit, which is because of some carriers which are already present inside the device, which just passes through the circuit and form the very small current, which is almost equal to the reverse bias current. Okay, so that also we can see with the device. Like if I take this dark, then of course when I am simulating my device with only dark, then there will not be any all these spectrum and all, and we can calculate our this is okay. Then we can put calculate single shot. So now this calculation is entirely for only uh, this one. Okay, I'll show you this IP characteristic. You can see. So this is IV curve. We can see that under no illumination there is no such current flowing. You can see it is the every all the IV curve is in the fourth quadrant, which is from below zero. So the current is infinitesimally very small. Okay, so that also is possible with SCAPS. Fine. Now, uh, yesterday I was talking about this series and shunt resistance. So today we will see that there is effect of having it and not having it in our simulation. So let's say I have taken this IV characteristic for the same device, and I am taking it because I know that VOC is around 1.5 or 4. I'll take it up to 1.5, and I'll check on stop after VOC. So it will stop after VOC. Okay. One more thing. When you are switching from 0 to 1.5, we also have this freedom of selecting what should be my increment voltage. Okay, then let's calculate this. So yeah, this was my the last current. Now you can see that this is very similar to the reverse biased current, which is almost zero for any device which is in reverse bias. So the same sort of current flows when we simulate our device for no illumination, right? The dark current. Like if you all can remember the equation for this current in this I is equals to I naught e to the power eta by kt. So that I naught is something which is reverse biased current or this dark current in case of solar cells. Okay, so I was telling that you can see these are the values, and now what will happen if I do not check on this series and shunt resistance. So let's see, I'm not taking my series and shunt resistance and then calculating this. There will be a minimal change for sure, showing that you are not simulating a very practical solar cell, because whenever we fabricate any solar cell, it is by default that it will have a series resistance and shunt resistance. This series and shunt are basically because of the various losses that occurs in a solar cell because of the defects we have. So now if I check on it, you can see there is very minimal change in this. If you remember, this blue color graph was my earlier graph, and now this green, sorry, the green color was my earlier graph, and now this blue color. So there is a bit shift in IV characteristics when I change that, whether I'm opting for any shunt resistance or current or not, a shunt resistance or series resistance or not. Okay, so we really need to think about what values for these series and shunt resistance we need to take care, so that we can get the almost very nearby simulations. Okay, so if I see this, yeah. So almost every aspect we have taken care here. Now, one thing, this temperature. Yesterday we talked that mostly solar cell works in an environment or an ambient which is at room temperature. Okay, so all these simulations are done at 300 Kelvin. But as we all know that solar cell cannot be only at this room temperature, because it is always kept at outside our home. So we need to incorporate those actual values of temperature as well. Like in a dark sunny day, the temperature rises up to 40-45. So if I want to research on a certain solar cell to work in this that environment, I cannot simulate my software like my solar cell for that 300 Kelvin. I need to inculcate those values as well. So the software gives you that freedom as well, that you can change this temperature value. And of course there will be change in the parameter value. So whenever I'm saying parameter, I really mean this voc, isc, fill factor, and power conversion efficiency for the solar cell. So these values changes when we do change this working point, which is specifically this temperature. Okay, now today I'll also show you what are like yesterday we primarily talked about the IV simulations. Okay, now whenever we simulate any device in SCAPS Bundy software, we get this like this IV domain was there, wherein we can see the IV characteristics. Then there are certain recombination current also, and we'll come to this later on. And then energy bands. Yeah. So these are the energy bands. We all are interested in plotting the energy bands whenever two or more semiconductors get in touch with each other. So we can see here, uh, like uh, from 0 micron up to 2. Like if you remember the device that we are working on has a thickness of its absorber layer to be 2 microns. So there is change in the band diagram at 2, because from 2 onwards there is another device, sorry, there is another material which in this case is zinc selenite. Okay, so this band diagram can also be analyzed, and so we can take this data out, show data. So if you see here, so again I'll let you understand this graph I was working with. Okay, which is our energy band diagram. So like whenever we simulate anything, we need to plot those data, and let's say we are working for certain publication, like we want to publish our work that we have done. So definitely I need to get this graph as well, right? So I don't know, like most of us do not prefer having this complete diagram in our like papers, because it's not that clear, and of course it doesn't meet all the requirements of of certain journal or conference you're working with. So in that case we really need this data, and then we can plot it in our own domain, so that you can get it from this show data. Okay, so this show data will show you all the 4 parameters of this console. So if I put this, so this is what you can see. This is my conduction band, Fermi level, and then EV level. So basically the diagram which is here is plotted based on these values. Okay, so these value we can fetch, save it somewhere, and then plot it accordingly. Similar way, okay, that show data will have all the values, not only this, but at the interface also and everything. This all data we can take and then plot accordingly. Okay, similar way, if I go for this IV characteristic, I want to plot this IV characteristic in one of my own software. Like mostly we all researcher prefer like there is one software, Origin. So Origin needs data, and then we can plot the same plot there, and then we can make some more like if I want some borderline, some like some good like visuals in my plot. So the for that I need the data. That data I can take it from here. So here you can see I have voltage, current total, current recombination, and everything. You can take this data, and then accordingly you can plot it. Okay, so I was interested in telling that we need not to take these screenshots in our publications. We can take data from here and then further get it plotted in any other software. Okay, although they have this option of save graphs with PNG or JPG. So if you are comfortable having this, then you can see on this panel we have the option of saving our image as a PNG or JPG or BMP format. Mostly we prefer having in JPEG. So they give your quality also, and then you can check on whether you want the whole IV panel or just current density. Of course we need current density, and then you can save it. They will ask you where you want to get this. So I just renamed this there and saved it. So if I go back there, I can show you. Basically, this session is primarily focusing on how to use the software, how all you are using. You can change it accordingly. So I'll show you what has been saved. So the same picture there we took it. So yeah, it is not that bad. If at all you want to use it in your publication, you can use it. So you can see that it is completely the same diagram that we have simulated there. Of course, when we are uh, doing some other simulations also, we can remove the previous one, but it is just for you to understand that that image can be saved directly in SCAPS folder wherever you want to, and then later on can be used as a image in your paper. So it's not that clumsy, and you need not to take the screenshots. You can just save these images also. Okay. So many times whenever some bachelor students work on, they prefer not to plot it in some other high-end plotting softwares. They can use this also, like in many of our literature papers I have seen such images being used there. Okay, so now going back to our software. Okay, similar way, we can plot this recombinations also. So many times we are interested in to plot how recombination is occurring inside the device. So such things can also be taken here from. Okay, and okay, going back. Okay, now let me. Yeah, so I'll show you one thing. And okay. Yesterday we talked about changing certain parameters. So we talked about changing this thickness. Now there is one more such parameter which actually changes the complete performance of the device, which is this density, like what doping density you are using. So for my work, I had optimized it up to 5 is to the power 15. So let's say I do not know that what will be my optimum value for this donor density, sorry, acceptor density. I change this to 5 raised to the power 10. Okay. And then I'm calculating single shots. I'm using my series and shunt resistance. I'm giving it at light, and I'm more interested in IV characteristic 1 to 1.5. Okay. And then calculate single shot. That's done. So you can see now my third simulation is this, I think sky blue color we can say, or cyan color. Sea green also is a good name for it. Okay, so this is my third simulation. You can see that this diagram, this efficiency got changed. That is 16.28. So, a part of my work also, and mostly in all the papers that I have gone far so far, we do get this optimization. Like yesterday, somebody was asking me that this how to get the optimized value. So I was telling it that it is a trial and error method. So this is how it goes. We can change one by one values of all. Let's say we first focus on changing the thickness. Okay, so when we are changing the thickness, we focus on how this change thickness will affect my device. So I'll change my thickness for let's say we'll start from 1 micron up to 1.5 to 2.53 whatsoever. Let's say we took 4 or 5 such simulations, and eventually we obtained that at 2.5 at 2 microns my system is working well. So now I'll fix that value to 2, and then if the okay, thank you. Okay, so yeah, what I was telling is once we optimize the thickness of one of the layer, we can move on to other layer and optimize the thickness. Then the optimization also can be done on these parameters also, because I told you that the properties that we as a researcher put in there, these are all fixed properties. But this doping density is not a fixed thing. It is something that as a researcher we can change, or as a industry person who will be fabricating the device we can change. Like we can have holdover over what kind of doping or what sort of doping we have to do. So we can optimize that by changing that values also, and eventually getting a value which is giving the maximum parameter values. You can see I changed it from 10 raised to the power 15 to 10 raised to the power 10, and I got that my efficiency got decreased, which means although that 10k power 15 was an optimized value which I received by doing my hit and trial and multiple work. So let's go back and again. Sorry. Okay, so, yeah. So I can change it to 10k power 12, and if I do it, the simulation single shot. So again, there is not much change with 10 to the power 10 and 10 to the power 12, but yeah, there is change because we can see the two graphs separately. Although the value is very minimal change, but yeah, it do change. So with this, we can optimize our device, and then accordingly, once we get optimized all of the values like the thickness of this layer or any other layer, and then this density of one or other, because this is something which is fixed, which we cannot change. Also, many times, what is the absorption model that the software is using? So by default, the whatever model is defined in the physics will be used, but if you want to have certain other absorption file, you can change it from here. Like you can see absorption interpolation model, set absorption model. So here you can change, like they are using square root of under square root of band gap model, but we can change that also. So if at all it is required by the user, they can use it. Okay. Set. Okay. Now one thing, when we when you just see this, the illumination is coming from the right. So if I show you my slides, like if you remember, there was the sun rays coming from the top side where my window layer was, if you remember. So here my window layer is that zinc oxide and zinc, like aluminum doped zinc oxide and then intrinsic zinc oxide. But by any mean, if you want to change this or anything, we have that also, illumination from right or left. So here you can see that the illumination is coming from the right, you can change it to left, and the whole device will change. And you see, that now my illumination is coming from the left contact, and definitely there my first layer will be this absorber layer. Okay, so this is also a part of our research if somebody is interested in. One more thing, as we all know that solar cell is a device that produces electric current, that we all are know, that whenever a sunlight falls on a solar cell, it creates a electric current, which is the very basic definition of any solar cell, be it first generation, second or third generation. The basic diagram, basic definition says that it develops or it generates electricity when it is put in solar cell radiation. So what happens that if you remember this getting simulated. Okay, the same. If you can see here, my IV characteristic is lying in first quadrant. Okay, but as a student or as a reader, if you remember that the solar cell quadrant is always fourth quadrant. Okay, so we convert it this way. If I go this set problem, so what is this consumer and generator? We just check on generator value, but if I go with this consumer, my IV characteristic will be actually the same that we study in our courses, because we know that the multiplication of IV must be positive to provide to put it as a generator. So when it is in first quadrant, it is positive. So now you can see, yes, this IV characteristic will be exactly same that we got it from our previous simulation, but now it will lie in the fourth quadrant. So that is the difference for getting it as a generator or consumer. Okay. So now I believe that yeah, it is all that one should know in order to use the software, specifically this one, this SCAPS 1D software. Okay, I have talked about all sort of all sort of values that needs to be put on, and what all sort of data that needs to be filled in before getting this simulation, specifically for solar cell, and then getting our simulation done. One thing also I would like to put effort on, like in all my simulations I have shown you that we got IV values, like the simulation went well. Okay, but there can be cases that you will not get the simulation done. I'll show you one of such case. Let's say I am putting it as 0.5, sorry, and then calculate single shot. So what I did is I know that my solar cell that I am working on has a VOC of around 1.2 or something. But now I just checked on the voltage up to only zero point 0.5. So in that case, what will happen? Just see. I'm not getting all my values because VOC has not reached, so it will not be shown. So this is a wrong simulation. Okay, even if you are getting this efficiency as 10.6, but that has no meaning when we do not have other three parameters, other two parameters. Okay, so this I wanted to tell you that this is called as certain error in your simulation. If you are getting such simulation results, we really need to take care that how to rectify that. Sometimes we get convergence error also, like I'll show you how does this convergence error occur. Let's say we are in this IB characteristic, and okay, in my problem, let's say I have used 5 microns. Okay, I'm telling you what are the problems that you may encounter, because when I was learning the software, there were like for around 15 days I was not getting any simulation result because of this convergence error, and that time I was not aware of. So what is this convergence error? Like I have changed it to, let's see whether it gives you that error or not. What I did is the standard value that we received, we got it was 2 micron, but I changed it to 5 micron. Let's see how does it all go. But yeah, I got the values. Again, it's error because it has not got it with the point. If I improve it to 1.5. Okay, since I'm using a device which is actually correct one, so I'm not getting that convergence error. So what I wanted to tell you that many times you will get a pop-up message here, convergence failure, which means that the certain values that you are using in your material properties or in this panel is not meeting the requirement of the simulation, and that is somewhere we do delve into the research. Okay, so if you get that error, don't think that there is a problem with the software installation or anything. It is just that your device is not in compliance with what is required to get the correct simulations. Okay, getting different values and optimization is a different task, but giving a value which is not at all allowed, which somehow doesn't allow the equation, the physics behind the software, which is like one dimensional solving equation, then in that case it will show you error, which is in the form of convergence error. Okay, so that's all from my side for the software. Now I would love to answer your questions, like if any of you has installed the software and has got certain such things, some error or something you want to ask, because I believe that whatsoever is required to run this software is being taken care in the session, like yesterday's session and today's session as well. So if you feel that there is something that I can help you all with, then we can have words with that. Okay, so okay. There are certain questions I didn't check it. So Mr. Rahul Kumar is asking me, sir, why is only one interface considered for the current device? Okay, okay, I'll answer this question, Rahul. Sir, actually, I told you that we are interested in putting my device to the more physical or more practical way. So for my device, it was absorber layer and the, you say, buffer layer, which is the PN junction formation. So I was interested in the dynamics or the physics at this interface only. Like when we are working with the window and buffer layer interface, that has nothing to do with my electron hole pair generation, and that will definitely will not affect my much more physics for the solar cell working. But when it comes to absorber and uh, buffer layer, I am interested, so that's why I have taken this one interface. But let's say like I have seen that in my previous like before me there was a session on perovskite solar cells. So when we work with perovskite solar cells, there are 3 layers involved. Okay, so for that we do consider 2 interfaces as well. Okay, so that completely depends on what solar cell you are working with. I hope, Rahul, I'm clear that for my software, for my device, I was using PN. So definitely, I was interested in the dynamics at only PN interface. But if you are using multiple, because we can see in SCAP there are 7 layer possibilities, and if all of them are semiconductors, then definitely you need to put on some more interfaces. So that's why you can see in the software it is not only one place where this is available. I'll just put, just give me a minute. Yeah, if you see this, it is not only between these two. So now I'll once a very good question. Like, for my first layer and second layer, this is my interface. For my second and third, this is my interface. For my third and fourth, this is the interface. So if whatever devices you are working with, if these two layers are certain layers which can have change in its properties at the interface, you should incorporate those values in your interface domain. Okay, because we want to make our device more and more practical. So it is very much required that we should incorporate all the defects that will develop around this interfaces. But for my device it was only one, so that I have taken only one. Okay, let's see what other questions are. Can you show the corresponding electric field profile across the length of the device? I believe electric field is not being shown here yet. In, like, I had no idea. I didn't work with electric field. But actually, there is a software. I think console is there, wherein we can get that electric field change. But yes, if you really want to calculate that, we can do with some other software. Like, we can take data from our simulated device, like IV characteristic, and I think if I have that IV, we can change it according to some formula or some equations, but which I have not done for sure. But definitely that can be used from the data we get here, and plot it somewhere to get the electric field. uh, which is okay. So Kanishk Mazumdar sir, I have answered your question. Then there is Surya Karthik, and which is the best position for the absorber layer in the solar cell? Um, I do not get this question. Like, which is the best position? I mean, you are asking that in this. Once again, I will go back. You are saying that where I can put. Okay, I'll first change it. This was my device. So yeah, what is the best position? No, it is not up to us to change the position depending on what device you are working with. But for my device, I was talking about, I was working with AMTS, so definitely I have to take this PN type materials only. I cannot change this position here. But yes, if for my research I found out that certain different material can be put before getting it into the contact, I can add that layer here, and then in that case my this absorber level come up, not down but up. Okay, but I mean to say that the whole physics of solar cell works with these two layers only for this specific device, which is this it being p type and it being n type. So when this is pn, this is these two layers are responsible for the whole this solar cell performance. I have added these two layers just to enhance the performance. So if you somehow feel like nowadays molybdenum sulfide MOS2 is one such material which we use before any contact, and that is just to enhance the property. So that is also, that's something research we work on. If you get any layer that can be used in between or above it or below it, then you can definitely use it, as long as it helps you in improving the performance of the device. Okay, so yes, there is no fixed position for absorber layer. You can change it as per the requirement. So any more question? Does anybody install the software, like having my previous session yesterday and then coming to today's session? Anybody tried having the software installed? Like, did you get that link I shared yesterday? And I hope from there we can install it. So, any problem in installation? Okay, I hope no problem. So, can I get some more questions to strengthen the understanding of the software or some other thing?
You can unmute your mic and you can ask, or you can put your question in the chat box.
Yeah, I'm reading chat box. So if anybody has certain sort of question regarding the installation or where to get data and everything, then we can show. After that, I'll show one of my work. Like, definitely, I'll show my one of my paper, wherein I'll show that how SCAPS has evolved, and how data, and what sort of simulation we should try when we are learning, when we are in the learning phase. So I'll show that part if I'm not, if I do not get any question in another 1 or 2 minute. I'll just wait, hold on for another 1 or 2 minute, and then I'll show you that for a person to start work with SCAPS, I'll show you my first paper where I have started working and what sort of things that we can use, like what we should work on. Okay, so I believe, yeah, like, if okay, one more thing, I'm dropping down my email address. If at all anybody wants to connect for working in this solar cell domain, specifically for SCAP software, I have dropped my email there. So you can connect me over there, or you can connect directly with the university and they can connect with me as well. So that you can do. Okay, so let me show you what are things that we should be working with when we have SCAP software. Okay, okay, just give me a minute. I'll share that part also. I think it's not visible. Not okay. So yeah, you can see this. This is one of my work that I have worked on. So there, the same kind of device I work with. So whenever you are like optimize, so one, but some, like, initially the people were interested in how optimization is done. So I have optimized my device based on these parameter. Like, firstly, I optimize the thickness, then optimize the thickness of buffer layer. Initially, it was how this optimization was done, that I told you in the software, that we kept on changing the values of these thickness, and then doing all the simulation, getting all the values, getting it in one. Then no, one thing that like when we change one width with another and then the third one, we can do that batch simulations also. In the software, there is when where it was single shot calculation, the second point was batch calculation. So if you set the values of thickness from 1 to 3, it will do all the changes at a step size of zero point 0.5. Let's say you have mentioned there, and it will show you all those values. Either it is one time one, like you change the values of thickness one by one and get the result, or you can get that batch simulation also. That I forgot while telling you the software. So that is also available there. Then somebody was asking me what is the position of flare. So I'll show you here that it's not only, if you can see, I have what I have done what instead of having only one absorber layer, I have stacked two such layers. So now the if you see this CZTS, now the position of CZTS layers come one ahead of its previous position. So that was a requirement of my like research, that what will happen if I get two layers of two different material both acting as a absorber layer. So that also I studied, and we got that values as well in our work. Instead of this, we can also get, yeah, all these four values, and finally the optimization is done. Okay. Similar way, in one of my more work, what I did is I got this work published in Solar Energy Journal, which is very noteworthy in the field of solar cell. So there, this was I think the same work which I was continuously using in our session. The device, the values. So you can see these are certain graphs. So I was telling that if you see these graphs I have plotted in origin, but that's not our concern here. My concern was, yeah, we can one get once we get that data from the software, we can use any other software and analyze other part of the data. So if you see in our software, I was telling that this whole mobility and electron mobility and defect density and everything was there. So all those you can optimize for a device that, like, why do we need this optimization? Because this simulation is something that helps us to get the actual value when we will get it fabricated. Like before fabrication, what are the values that we should incorporate in the device so that we can get the best performance of the device. Let's say if these simulations were not there, what would have happened? Like I fabricated one device and then I checked on its property and I found that it is not worth, it is not well, or it is not as per the requirement. So it's a complete wastage of our fabrication, which is really very cost effect not cost effective as well. It's very time taking and very much of intense research required. But when we have this simulation, what happens is we can get all those fabricated environment here. We just simulate our device, and if at all we find that my performance is not good, we do such changes in our software. So I'm telling you what is the importance of this SCAPS software. Like we can do simulation in one. If you have seen that not more than 30 seconds or 45 seconds it takes for one single shot simulation, so which is very good. Like even if, I don't know whether you all are aware that there are certain properties, there are certain software which require a lot of time to get one simulation. And that's because the Silvaco software that I was talking earlier, that also use this that also can be used for solar cell simulations. For that, simulation takes a lot of time because it solves the complete Poisson and the continuity equation in three dimension. But since caps solve only in one dimension, it takes lesser time. And I told you that it is well established that The performance of solar cell when solved in one dimension is pretty more good enough. No need to take for two or three dimensions because it's somehow more or less it is same. Okay, then also this these two efficient thickness I talked about, that we can change and get the values. And then you can see this graph. In this graph I tried changing the series resistance and shunt resistance also, and you can see that the IV characteristic kept on shifting either left side or right side depending on what values of series and shunt resistances we can have. So how this helps us in fabrication, that whatever series and shunt resistance values gives us the best simulation, we will try to have our solar cell fabrication in such a way that it will finally have that series and shunt resistance only. Okay, so like before doing fabrication we get to know what sort of properties should we incorporate in our fabrication of the material, so that we can get our required output. The same has been done for shunt resistance, and electron affinity was there. And then yeah, I also talked about this just see this band diagram. If you remember that it was simulated, after doing the simulation we got it there in our SCAPS also. So from there I just taken that data and then solved it here, like used another software known as Origin. It is just plotting software. It just takes the data and plot the data. So you can see the same can be drawn here. So there the clarity was less, but yeah, we can enhance that clarity and understand that why such deep changes and everything are done. So again, it is the beauty of SCAP software that it does not only give you the images or the simulation results in image form, but also it gives you the data so that you can use that data and analyze it for your requirement, and then further use in your findings. Okay, then CV characteristic and CF characteristic, I showed you there that there are certain these possibilities also to be used in the software. Like if you want, if you are interested in calculating the CV and CF values, then we can use it there. Also you can see here I have that illumination intensity. If you remember, that was for SCAPS. Sorry, that was for AM 1.5G. It was 1000 watt per meter square. That also we can change and find out that which is the best suitable illumination for performance of solar cell. So that part also can be analyzed. You can see that one single software is giving us so many data which can be used to analyze so many different findings. That 1 by c square also we can plot. Somebody was asking initially that how temperature works. I have studied that also, and the temperature somehow changes the open circuit voltage. So not only 240 Kelvin but also up to 360 Kelvin I studied actually furthermore also, but the changes were not that much. So we plotted it here. We can see that actually there are two materials I have worked with. So these two materials got a shift in their VOC values when we changed from 240 EV to 360 EVs, sorry, Kelvin. And then recombination also, if you remember, and the last simulation portal there was this recombination profile also shown there. So that also can be analyzed. I have taken that data and plotted it here and got finally the values. So that's all. So this was all about the various result analysis that can be done by taking the data from the SCAP software.
I'm not quite sure how to help you with that.
Sorry, I forgot to shut my Alexa. Okay.
Sir, there are
Okay.
few more questions in the chat box.
Yeah, sir. Now I can see a lot of.
829 around.
Yeah. So Rahul. Okay. Okay, Rahul. Okay. Yeah. So Rahul is asking, sir, under what condition can a buffer layer replace ETL and HTL in a device? Rahul, again, like we this buffer layer I was talking was in reference to CZTS or this thin film solar cells, but this ETL and HTL concepts come into picture when we work with perovskite solar cell. Okay, so when you are working with perovskite, you have to take care of ETL and HTL layers and then absorber layer. But when we are working with some PN junction type of devices that I have worked with and that we have all talked about, then you have to take care for buffer. There is no such replacement required. These are two different entities required for two different type of solar cells that we need to work on. Thank you so much, Sudhakar sir, for your kind words, for saying thank you for saying that the session was good enough. Okay, how does a passivation layer affects? How does a passivation of a layer affects VOC, JC, and fill factor, and what is its ideal thickness? So, of course, passivation is something you're talking, which is something a characteristic which we actually take care when fabricating the device, but it has nothing to do with SCAPS, because in SCAPS, once you define a layer with its property, it is that layer, whether it is passivated or not. That software will not take care of. But yeah, since you have asked this question, what is it ideal thickness? Again, if you want to understand what should be the ideal thickness of that passivation layer, then again you have to put those values, those property values in SCAPS, and then optimize your device, and then you will get what is the ideal thickness. Either you just go for fabrication and find out that what could be the final ideal thickness, or you can just get that value in the software and simulate it for multiple number of times, and then you will get the ideal thickness values. Okay. Uh, can we calculate material properties using formulas and use them in SCAPS 1D? Yes, very good question. It is. You just reminded me of my PhD days when I was started when I had started working. I had this intent in mind that let me use some formulas and use the properties and then use those properties in SCAPS, because in SCAPS, if you are using any material which is well established, you will get that you will get its literature value in the literature, no problem. But if you are using any new material, so you need to get that value, means all those eg, ev, nc, nv, all n, nd, all values. So those values you can do, yes. Certain formulas can be used, but if it is a novel material, like any material which do not have any such properties, then in that case, we go for this DFT simulations, like density functional theory. There we get the properties of the material. Nowadays, machine learning is also one such method to talk about the new properties of new materials. So from there also you can get and then use it in the SCAPS. For using SCAPS, you need the data. That data is the property of the material. So that is your business where you will get that thing in or not. Sir, I prepared a device with the structure CUI, that is copper iodide with CH3 and H3. Okay, it's perovskite. Okay, and I am getting a convergence failure at lambda is equals to 300. So no QE calculation was done. Okay, so Rahul, it's better like we get in a like one-to-one conversation with the device, because until and unless I see what device you have formulated, what are the properties you have entered, will it match with the device property, sorry, material property or not? So all those things, because once you say that it's a convergence failure, then it shows the surety that there must be some error in putting the material properties or the parameters for solar cell simulation. Okay, So I would request you to please connect with me, like after the session, some way or the other, and we will have discussion on. I'll see that if you can share that device with me. I'll see what is the problem with the device, and we'll let you know. Because without saying it, yeah, I cannot say, I cannot comment, but definitely, if it is a convergence failure, there must be some problem with the values of the material that you have put in. So I'll again share my ID here. We can connect and resolve your problem. And I'm telling you that once you start working with the software, you will get n number of convergence error. I was getting it, and there was nobody to help me out, because it was something that I have taken from the very first time in my class, in my batch. But yeah, with like a month or two, I got all the simulation because I understood what are the problems. It requires lots of literature survey to get the exact values, because sometimes what happens in some publications, by some error or something, let's say I'll tell you my case. The electron affinity for the material was, I remember, 4.1 or 4.2. Okay, and by some error or something in the paper that I was referring to, they have put it as 4.6, and I was putting 4.6 because that was the paper I was referring, and I was not getting the it was all showing me error and every time. Then my supervisor sir, I'm really grateful to him that he just told me, Ashutosh, please go through all the properties from different literature, like let's say band gap of a certain material in x number of paper, and just find out that which one is correct, because many times certain typo error occurs, but for somebody who is reciprocating that paper will get some problem. So I did that, and once you read three or four papers for one property, you will understand that which one is correct. And by doing this only, you will get one device correct. And let's say I was working with one material, so it took me 2 3 months to get that model developed. And once you get a complete clear simulation, correct simulation for a device, now that device will be with you for your whole life. I am telling you that I it took me 2 3 months to develop that first device, and after that, that device was working. So I kept on changing new materials, and it all worked. So for the it's not, it will not be like for the very first time we get some data and it will work. No, yeah, you need to do a lot of literature. And even like if I am sharing my device, it will work with you because we are in one-to-one contact. I'll give you the correct data, but when we put these data from literature, then sometimes we make mistakes, sometimes the data is not correct. So our software will go to work only with the correct data. So many times we need to work for few number of more literature and then get those values. Surya Karthik sir is saying that, okay, now before that, Ghate sir is saying that, sir, if we do not know EG of a new material, how to start? Sir, if it is new material, it has to go through some DFT simulations to get the properties, because until and unless I do not have the property of the material, SCAPS will not take it as anything. Like if I give any value, it will give you the simulation, but definitely it is not as per the requirement of yours. So and if you are talking about any material which is already established in literature, then we need to search for that material, get it the EG value, and then we'll start. So to start SCAPS, the first thing is to get its material properties. After, so I hope, sir, this is what you asked, and this is what I answered. Then Surya Karthik sir is asking me, sir, I would like to seek your guidance on solar cell simulation using SCAPS 20. I must tell that I will be really, really thankful to you if somebody comes from this crowd to me, so that we can work together. I'm not saying that I'll be helping you out. We both will work together, because, of course, somehow I know more of SCAP. That's okay completely. But we will work together, and I will definitely help you out too. If you are a starter, like if you are learning starting this software for the first time, definitely I'll help you. And if somebody is there who already knows the software, then we two can work together and get some more research in the domain. Because I have worked with this single junction software that I have shown you here, single junction device. But nowadays there are a lot of tandem devices are there, multiple layers devices. I have done that multiple layer also, but not tandem. So if somebody is interested in having tandem solar cell simulations, we can work together and get some good research. Okay. So thank you, sir. Definitely, Surya Karthik, sir. I have shared my email ID. Just drop me an email and let's get connected and start working on. I'll definitely help you out, and we'll work together to get some fruitful results and fruitful research as well. Also, Ghati sir saying thank you so much, sir. Sir, I hope I have answered your question, and if at all any such clarification is required regarding the simulation or the usage of the software, I will be loving to do that in person to person also. So, any more questions if I can have, or that's all for my from my side. And Nitin sir is there.
Uh, I think no questions are there. Answer has already dropped the mail. So those who want to ask anything or have any doubt, they can mail this, sir.
Thank you so much, sir.
Thank you so much, sir. Thank you so much. On the behalf of management, principal, and the AICT Atal FDP organizing team of AC Patil College of Engineering, I express my deepest gratitude to Dr. Ashutosh Srivastav. Sir, your talk will greatly benefit the researchers and professionals who wish to begin their work using the SCAPS 1D simulation tool. Thank you so much, sir. Thank you.
Thank you, sir. Thank you all for listening me and giving your valuable time at this point of time at like around from 7:30 to 9 o'clock. Thanks a lot. Thank you, sir. Thank you for inviting me for this session. It really helped me to just rebrush my expertise and all. So thank you all. Thank you, sir.
Thank you, sir.
Uh, Over to
Thank you.
Gati, sir. Yeah.
Thank you, sir. Thanks a
Thank you.
lot.
Thank you.
Professor Patil, sir, will you please stop recording? Dear participants, tomorrow we will have three sessions. First session will start at 2 o'clock, so 2 to 3:30, first session, 3:30 to 5, second session, and 3:30 to 5, second session, and 5 to 6:30, third session. After that, uh, just after that, we will have maybe at 6:45, we will have valedictory program, and there will be certain instructions regarding your quiz as well as feedback. Okay, so thank you very much and good night to all.